So that brings us to topic 2. Good work, everyone. We're doing well, getting through some of the content, which is awesome. If you're still tuning in, thanks so much. And again, feel free to pop any questions you have in the live chat as we're going along. But yes, we are up to topic 2, which is awesome. Time series data. It is a whole new topic, but the awesome news is that a lot of it is actually quite similar to topic 1, bivariate data, because time series data is still bivariate data. It's just a special kind of bivariate data. And the kind of like the defining thing for time series data is that it's bivariate data where the explanatory variable is always some measure of time. So what happens is a variable, our second variable, the response variable, is recorded at successive time intervals. And then we can graph that on a time series plot and look at how it changes over time. So we could look at temperature over the week. We could look at TV sales over the week. We could look at temperature over the year. There's all of these different things that we could look at and how they change over time. So again, with bivariate data, our EV and our RV, our explanatory variable and our response variable could be like a massive number of different things. And here our response variable can still be like anything that we're looking at, but the kind of like the different thing is it must be looking at how it changes over time. So our explanatory variable must always be some measure of time, how something changes over seconds, minutes, weeks, months, years, decades, any measure of time. We're always interested in how our response variable is changing. So for example, temperature and ice cream sales. This actually is not an example of time series data because we don't have an explanatory variable that's a measure of time. But if we looked at ice cream sales, like the average monthly ice cream sales over the year, then all of a sudden it is time series data because we're looking at how ice cream sales change over time. And then we're looking again at those patterns, relationships, associations. So we're thinking about like, oh, that's so interesting. We're selling a lot more ice creams in December and we're not selling a whole lot in July. Why might that be? It's related to temperature most likely. But again, it's got to have some measure of time for it to be time series data. And we'll have a look at an example just in a second, but another thing I want to flag is that we do connect the dots in a time series plot because time represents a continual, precise, linear, and unchanging relationship. Whereas when we had our bivariate numerical data scatter plots, we just had heaps and heaps and heaps of points everywhere, so it made like no sense to connect the dots. But with time series data, we normally just have 1 point at each time interval. And again, that's like precise, that's a continual, linear, and unchanging relationship. So we can connect the dots, like in the example we have here. So this look, again, time series plots, very similar to scatter plots. We're still graphing bivariate numerical data, but again, our explanatory variable, which is always graphed down the bottom, must always be some measure of time. And here, that's by months. So January, February, all the way through all of the months. And what we're looking here, this is actually a specific example of seasonality, which we'll get to in a second. But what this time series plot is about, it's about the mean or like the average temperature per month. So our response variable, which is graphed on the y-axis or the vertical axis, is temperature. So here we're interested is how does temperature change over time? That's what we're looking at. And interestingly, we can see the temperature is higher, like around January. It's lower around July, and it's higher around December. That makes total sense because of like the seasons that we have here in Australia. So you can start to see this, like how our time series plots are really, really helpful for representing that time series data. So again, it works the exact same as a scatter plot in how we plot the points. Every point represents like a time element on the x-axis, and then the response variable will be plotted on the y-axis, and so the dots will all represent that. And again, the main difference with a scatter plot is we normally just have like 1 dot like per time point, and then we can connect them because of that continual, precise, and unchanging linear relationship. And so when we're actually discussing time series plots, when we were discussing what was it? Scatter plots. We talked about the nature, the direction, the strength, the form, the outliers. That was the language we were using. But we kind of switch gears a little bit when we're talking about time series plots. There's slightly different language and features and patterns that we actually look at. And the syllabus tells us what kind of terminology we're going to be using. And again, you can download these slides from the resources tab if you did want to use that link to go to the syllabus. So we can see here that topic 2 of unit 3 about time series analysis is about describing and interpreting patterns in time series data. So this is something that you need to be able to do. So first bit, you need to be able to actually construct time series plots. So again, we went over briefly some of the key features. You need title, axis titles, units, the dots, connect the lines. That's all of the main things for time series plots. And then this next dot point is saying you need to be able to describe time series plots. And this tells us what kind of language they're going to be looking for by identifying features such as trend, which is like a long-term direction, so a long-term increasing or decreasing trend. Seasonality, which is like systematic calendar-related movements. We're going to define all these in a little bit more detail shortly. Irregular fluctuations, which is unsystematic short-term fluctuations, and recognized outliers, which are once-off unanticipated events. So, trends. Again, like what the syllabus said, that's like the overall tendencies for values to increase or decrease over a period of time. So here we have an example of an upward trend, which is reflected by this trend line here. And then here we have an example of a downward trend, because we can see that over time, so as time passes or as time increases, our response variable is decreasing. So that's when we're getting a downward trend, like that negative relationship. But here's a positive trend, because as time is passing, our relationship is going up. The third one I'll draw your attention to is the fact that we can also have mixed trends. So it might go up for a time period, down steeply for a time period, and then level out by a time period. And you can also reflect that using multiple trend lines. So that's something to keep in mind as well. So again, that's what a trend is. And we can use trend lines to identify them, like we've done in these examples here. The next one, seasonality. Same graph that we were looking at a little bit earlier. So seasonality is kind of any patterns that we see with calendar-related periods or calendar-related patterns. So if there's like a weekly pattern, a daily pattern, or a seasonal pattern, like that's all what we're looking at. So patterns are often, these kind of patterns with seasonality are often quite predictable. And again, if we're discussing a time series plot, teal is actually a really good structure to come back to because T, we're thinking about like our topic sentence. What is it that we're discussing? What have we noticed? E is evidence. Whenever you're like kind of maybe giving a bit of a paragraph answer on like describing what you're seeing, describing like what you're seeing in your like time series plot, it's important, really important to make sure that you're actually giving evidence. And the evidence that you need to give is like the numbers and the patterns and the trends that you're seeing in your time series plot or like your time series graph. Like, you know, for example, I'm seeing like that low point around month 6. Like those are all the type of things that you're going to be talking about. So seasonality is all about those patterns that are like related to the calendar. So here we're definitely seeing like a very because we're looking at like the mean temperature per month. So we're definitely seeing seasonality here because we're seeing a pattern that's really like related to like the months or like the seasons, which you describe that as like a quarterly pattern because the seasons are about the 4 quarters of the year. And seasonality is often quite predictable. Because on the other hand, when we have cycles, they're very similar, but there are some key differences. So cycles, like we said, they're like seasonality, but the main difference, which is really important to keep in mind, is that with cycles, again, predictable patterns, but the period is usually a year or greater, and they're usually less predictable than seasonality. So with cycles, we're actually looking at really long-term trends and patterns. So this could be like, this could be months, or this could be years passing. So we're looking at really long-term repeating patterns and trends. And again, they're usually a bit less predictable than seasonality. So yeah, that's really important to keep in mind, the difference between seasonality and our cycles. The next thing important to be able to discuss is structural change. So structural change is where we see like a significant change in the established pattern that was previously consistent in our time series plot. And it often does result in a new trend. And it's often like caused or reflected by like significant like external events. Like if like the economy crashes, or if there is a war, or if there is like a snowstorm, like that's all gonna have a serious impact on if we're looking at like temperature data or financial data. So you can see here in this example, we have like this really strong, like steep increasing, like positive increasing trend and pattern. And then we actually have a structural change around time 13. So again, it could be months, days, weeks. This example doesn't specify. You can see that's actually resulted in like a new trend or pattern. It's kind of like it does decrease a bit and then increase a bit, but it's fairly level compared to our previous pattern. So structural change, again, it's like that significant change in a pattern that was previously consistent, and it normally does like have an external cause. The interesting different thing is outliers. So what's the difference between outliers and structural change? So outliers are a single unexplainable point that stands out from the rest of the data. Whereas you might have noticed that when we had our structural change, there was that big change, and then it continued with a new pattern. However, here with our outlier, we have a single unexplainable point that stands out from the rest of your data. So this is going to be really important to take into consideration when we are discussing like our time series plots, because that is a factor that's like very heavily influencing it's very much influencing our data, and it's something to be able to discuss when we're just looking at like patterns and what we see. Next is irregular fluctuations, which is essentially everything else. So all things unpredictable and unexplainable that don't fall into the previous categories. The reality is that in any real world data, we're going to have irregular fluctuations, like the random up and down. That's not this beautiful, predictable and smooth patterns, because irregular fluctuations, those random changes, are going to happen in temperature, in sales, in almost all of the data that we look at. So that's something to keep in mind as well. However, sometimes we do not want the irregular fluctuations to skew our data. Sometimes these irregular fluctuations can actually like obscure underlying trends. So we might think like, oh, there could actually be an underlying trend here, but it's just so obscured by all of these irregular fluctuations, like I actually don't know. So that's where the concept of smoothing comes in. So smoothing is like a concept or like a technique that's actually, the goal of smoothing is to remove the impact of those irregular fluctuations. So for example, like in that data we had before that had all of those random irregular fluctuations, the goal of smoothing is to kind of try and iron out those effects. It's like, hey, we actually really want to remove the impact of these irregular fluctuations so that I can actually see if there is any underlying trends or patterns. And there are 4 types of smoothing. So again, smoothing is a technique to overcome variation. Not so much seasonality, because we'll look at like deseasonalizing and reseasonalizing data shortly, but mainly irregular fluctuations. And again, it's about trying to uncover those underlying trends. So the 4 types are the 3 moving average and like the 5 moving average, or you might have heard it referred to as the 3 moving mean and the 5 moving mean. And we're going to have a quick look at those 2 today. There's also 2 other types. There is the 2 moving mean with centering and the 4 moving mean with centering. And I'll explain those shortly, but we won't really go into those 2 as much in today's video. But the idea of the name behind them as well, how they get the name, which will remind you how to apply the formula, is actually how many points that we're using to smooth each point. So to illustrate that a bit further, in the 3-moving average or the 3-moving mean, which is a type of smoothing, what we do is we take each value or each data point and we average it. So we take each value and we average it with the point to the left and the point to the right. So we're finding the average of 3 values. And because we take the point to the left and the point to the right, we actually can't smooth the first point and the last point because there's no point to the left of the first point and there's no point to the right of the last point. So we do lose our first point and our last point, but we are able to smooth all the values in the middle. So to illustrate the 3-moving average, here we have some time series data. I can see that because our explanatory variable is time, and then our response variable in this specific scenario is the number of houses sold. So in January, 12 were sold, February 8, March 7, but potentially maybe they've graphed this data and gone, oh, I think there might be some irregular fluctuations in here. So what we're going to do is we're going to use smoothing, in this case the 3-moving average or the 3-moving mean, to try and overcome this. So again, step 1, we cannot smooth the first month because there's no point before it or no point to the left of it to smooth it with. There's no month before January in this data set. So we have nothing to average January with. So we can't do January. So we move on to February. So to get the 3 mean or the 3 mean smoothed point for February, like we said before, we take the point for February, which is 8, and the point to the left or the point before and the point to the right or the point after. So to get the averaged point for February, we're averaging the values for January, February, and March, which is 12, 8, and 7. You've got to add all of those together, divide them by 3, which gives us 27 divided by 3, which is 9, which gives us our 3 mean smoothed value for February. And so you can kind of start to see how the process of smoothing plays out. By doing all of this averaging, we're kind of trying to remove the impacts of the irregular fluctuations. I think we have a graph coming up shortly that might help illustrate that as well. So next, I want to find the 3 mean smoothed value for March. So I'm going to take the values, the original values, not the smoothed values. We do all of our calculations with the original values of February, March, and April. 8, 7, and 14, and we add them all together, divide them by 3, again, the process of averaging, and that gives us our value for March. And then you go through and do the same thing to get the 3 mean smoothed value for April. We take the values for March, April, and May, average them, and that gives us kind of a smoothed value. So that's kind of how our process is working there. Very, very similar process with our 5-moving average. So how that works, same thing, except we're using 5 points. So we're taking the point, that's our point of interest, and the 2 points prior and the 2 points following. So we're using 5 points. So that also means we can't use January, but it also means we can't use February. And if we went all the way to the end of this year's data, we also couldn't use November and December because there's no 2 points after November and December. Same with our 3-moving average, except we just wouldn't be able to use December because we could average November, but then we couldn't do it for December. So 5-moving average, same deal. I'm taking the point for March and the 2 points beforehand and the 2 points after. I'm adding them together, I'm dividing them by 5, and that gives me my value for March. And then that's the process of it. So here we can really start to see what the effects of it is. So let's break down this a little bit more. So this is our data. Houses sold by month. Before we had it in a table, now we have it in a time series plot. It's visual, it helps us to see it. So the color coding is a little bit hard to see, but we can see here that our original, and we can also tell our original data point because it's got all 12, and we can tell this is our 3 mean smoothing because we're just missing the first and the last. And we can tell this is our 5 point because we're missing the first and the last two. But coming back to our original, we can see really clearly now that it's been visually graphed, all of these irregular fluctuations. Like there's not really much of a pattern going on. And when we have our 3 point, we've got to follow it kind of carefully. We can see this is our 3 point. You can kind of start to actually see that our data is in fact being smoothed. It's kind of being flattened, like the really up and down rough irregular spikes. Like it's actually kind of being smoothed and ironed out. Like you can actually see that process happening. And then when we come to our 5 point, and again, the more points you use, the more it'll smooth it out. Our 5 points, we can see it's even more smoothed. And now that we've done all of this smoothing, we can actually kind of start to see a tiny, tiny little bit of a potentially an increasing trend. Not a whole lot, but maybe a tiny bit. But that's just mainly to get you thinking in the groove of, okay, well, now that I've done my smoothing, we're going to look again for those trends and patterns. Is there now an increasing or decreasing trend that I couldn't see before because it was obscured by those like irregular fluctuations? But just to quickly illustrate the 2 and 4 moving mean with centering for you, I'd just like you to consider for a moment, what if we took the average of January and February? Because, if 3 moving average uses 3 points, 5 moving uses 5 points, 2 moving uses 2 points. Yep, that's awesome. That's a correct train of thinking. But if we take the 12 and the 8, we add them together, we get 20. We divide them by 2 because that's how many points we used, and we get 10. But 10 is going to lie halfway between January and February. So now we have this issue where we have this halfway between point where it's like halfway between January and February, and it's actually not on an original data point, which is what we want to see. So where centering comes in, gets a little bit more complicated, but what we do is we say, okay, if I take the average for these 2 months, perfect, average them out, get a halfway between average, and then if I take the average for these 2 months, add them together, divide by 2, get an average for the halfway in between, I now have 2 halfway in between averages. I have my value for here, which is 10, and my value for here, which is 7.5. And then the idea of centering is how we get it back to the center. So I've got these 2 in between points now, but to get the 2 mean smooth centered point for February, I'm going to average this halfway in between value with this halfway in between value. And then that's going to get us a point. So I'm going to average 10 and 7.5. And then that value answer is going to be our 2 mean smoothed value with centering. So there's and then you do the same with 4 mean, except it's kind of like you got to move it over a little bit more complicated. We won't be going through an example of that now, but it is the same process of I'm going to average the ones slightly to the left, average the ones slightly to the right, and then I'm going to average the averages to get back to the center. So you can kind of see how that's a little bit more of a complicated process. But that's kind of like the overview of it. And again, if you would like anything clarified, please feel free to ask in the chat. So awesome, that's our time series analysis, which brings us to seasonal indices. So first thing I want to clarify is, what is a season? Well, summer, autumn, winter, spring might be like our first thought, and that's totally an okay thing to jump to. That's definitely where my brain goes as well. And they are seasons, but they're not the only things that are seasons. So seasons are any breakdown of time with equal periods in the year. So a season could be days, a season could be weeks, a season could be months, a season could be quarters, which is kind of what we understand seasons to be for the most part. But it's not necessarily just limited to that. So if we could have a season for each day of the week, we might be looking at Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, that is still a breakdown of time with equal time periods in the year. So just how we looked at smoothing before, as smoothing is this technique to overcome the effects of irregular fluctuations, kind of remove the impact of that, see if there's any underlying trends. Now we're getting into something a little bit different. What if we wanted to remove the impact of seasonality? Potentially is what we're going to do here. So seasonality, again, that might be like, the temperature of various months throughout the year. That might be like sales on each day of the week. If we notice seasonality occurring, which is, again, those patterns within those like calendar related time periods, same thing that we're talking about here. What if we wanted to actually remove the impact of that seasonal, like remove the impact of the seasonality? That's what we're talking about here. So we can de-seasonalize data to remove the impact of season. We can re-seasonalize data, so getting it back to its original form. And how we do that is using seasonal indices. So seasonal indices scale information to reveal trends without the influence of seasons. So just like smoothing removes the impact of irregular fluctuations, seasonal indices like scale our information to reveal trends without the influence of seasons. My favorite example to kind of illustrate this is, are we selling more ice creams just because it's summer? Or if I removed the impact of it being summer or winter, is our business still doing well in spite of that? So if I remove the impact of seasonality on my ice cream sales, what trend am I left with? Are my sales actually increasing or decreasing overall? Well, we need to remove the impact of seasonality to kind of see that a bit clearer. So what are seasonal indexes? Seasonal indexes are a number representing the percentage above or below average that a particular season is. And it tells us how a particular season compares to the average season. And the average season is always 1. So the sum of your seasonal indices will always equal the number of seasons that you have. So for example, if we're looking at quarters, so summer, autumn, winter, spring, we will be looking at our seasonal indices should add up to 4 because the average of the season is 1. So it's going to add up to 4. Whereas if we're looking at months, our seasonal indices will add up to 12 because we have 12. But if that doesn't make sense yet, that's okay. We're going to go into that in a bit more depth now. So how to interpret seasonal indices. So a seasonal index of 1.3 means that the season is 30% above average. So if, for example, our summer ice cream sales seasonal index was 1.3, that means our summer ice cream sales are 30% above the average season. And say our winter ice cream sales might be 0.5, which means that it's 50% below the average season. Because mathematically, the average season is always represented by the number 1. And then when we're interpreting seasonal indices, we always interpret it in relation to the average. So again, for example, a seasonal index of 1.3, that's 30% above average. Average is 1. 1 is representing 100%. And like I said before, the sum of the seasonal indices will always equal the number of seasons. So with my ice cream example before, my seasonal index for summer might be 1.3 and winter might be like 0.5. And then, my other 2 seasons might be a bit higher or lower. And, some of them are going to be below 1, some of them are going to be above 1. But on average, it's still going to add up to 4 because that's just like mathematically how seasonal indices work. Because if the average is 1, then it makes sense that the sum of all of them is going to equal the number of seasons because, again, averages. So we're going to go through a quick example to illustrate that. And this question is taken from one of the NEEP QCE General Maths trial exams, which are available on 8R Notes Plus. They're super helpful if you're wanting to get in a few more like practice questions as well. But this specific question here that we're looking at says, the table below shows the number of houses sold by a real estate company in each quarter of 2018. So we know we're looking at quarters. So summer, autumn, winter, and spring. Again, time series data because our explanatory variable is the quarter, like the measure of time, and then the houses sold is our response variable. So we're being asked to determine the seasonal index for autumn. So first thing I'm noticing, autumn has sold 2,837 houses. So awesome, that's quite a lot of houses. But when we look at summer and spring are both in the 3,000s, but winter's also about 2,600. So interesting. Is my seasonal index going to be slightly above or slightly below 1? I'm not sure yet. We're going to have to calculate it to work it out, because we've kind of got these two that are a bit higher and these two that are a bit lower. So my thinking is that summer and spring will have a seasonal index above 1, and autumn and winter will probably have a seasonal index of below 1. So I'm thinking it's going to be A or B. And then D is just like completely wrong, because that to me looks like the average of all of the numbers, but we don't want that. We want the seasonal index. That's what we've been asked to find, which we know is going to be a number around 1. So I'm already thinking it's going to be A or B. So how do you calculate the seasonal index? To calculate a seasonal index, you take the value for that season and you divide it by the seasonal average. So we'll break down that a little bit further now. So again, our seasonal index, this is our formula, is equal to the value for that season, which in our case, the value for the season of autumn, divided by the seasonal average, which is the average of all of our other seasons. So the first thing we need to do is find our seasonal average. So we're adding up the value for summer, the value for autumn, winter, and spring, adding it up, dividing it by 4, and we've got 3,220.25. So that's our seasonal average, the average of all of our seasons, which ironically, they've tried to trick you there with D. That was what I was suspicious they were doing. So now that we've got our seasonal average, we can use our formula. So our seasonal index is equal to our quarterly value divided by our yearly average. You can see here, we've substituted into our formula. Our quarterly value is this here, which we've got here, and then divided by our seasonal average is this here. So that gives us 0.881, which is our answer for B. So our guesses were in fact correct, and we rounded to 3 decimal places because that's what all of the options were. So it made the most sense. But to conceptually kind of illustrate it a little bit further, this does make sense in my mind at least, and it's okay if you're still like kind of grasping it in your mind, because again, this is a Head Start lecture. It's just an introduction. We are going through this quite quickly, so it's okay if you do still have some questions about this. And again, that's what the live chat box is for too. So we have this number here. So the value for autumn, and this here is the average of all of the seasons. So I can already see that the value for autumn, I know that it's lower than the seasonal average. So I'm already kind of starting to figure out that I know my seasonal index is going to be below 1, because I can already see that my value for the season, it is lower than the seasonal average. So I know that it's going to be lower than 1, which is what we have here. And then, so that's the process that we've done there. And then to interpret that, or just to round a little bit to make things easier, so our seasonal index is roughly 0.88. Interpreting that based off the information that we've been looking at before, I can now say, having done this, that the houses sold in autumn on average is about 12% below average, because again, average is 1, and we've got about 0.88 is our seasonal index for autumn. So I can start to see that our values, our house sales in autumn are going to be about 12% below average. Winter's even lower, so that's probably going to be a bit lower below average. And I can see that summer and spring are definitely going to be above average. So you can see how we're kind of going to end up with 2 seasonal indices that are below average and then 2 that are like above average. So it's definitely going to, like, mathematically, it will even out. So they'll all add up to the number 4. And we can always check that if we need to as well.